In the cold silence of space, Mars, once seen as a frozen dead planet, yields its secrets. Its dusty, desolate surface of craters and towering dust devils hides clues to a vibrant past. Billions of years ago, Mars hosted vast oceans covering up to 20% of its surface, rivers wider than Earth's Mississippi, and a thick atmosphere rich with water vapor. Today, liquid water flows underground, concealed beneath ice and rock, as detected by NASA's Mars Reconnaissance Orbiter in 2018, hinting at possible subterranean microbial life. Its iconic rust-red sands, toxic yet familiar, are composed of iron oxide, giving the planet its distinctive color under a sun half the size of Earth's. Deep within its core, forces stir, suggesting volcanic activity once thought extinct, with lava flows as recent as 53,000 years old. If that idea gives you chills, you're exactly where you're supposed to be. Hit like, subscribe, and drop a comment with your theory. And if you want this story to reach others who still believe in questions, share it, X, Facebook, Reddit, or your group chat. You're helping light up the dark. Thank you for being part of this. This is not the Mars of textbooks. It is a world of contradictions, once Earth-like, potentially key to humanity's future, as a second home or gateway to deeper space exploration. With NASA's Perseverance rover drilling into ancient lake beds and China's Zhurong rover analyzing mineral-rich plains, we edge closer to unraveling Mars' mysteries. What awaits as we uncover the truth about a world hinting at life, water, and echoes of a lost history, all under the watchful gaze of its two small asteroid-like moons, Phobos and Deimos. Part 1. The Deception of Color. Mars is not red. From Earth it appears as a fiery ember, but that rusty glow is a thin veneer of iron oxide dust. Its surface radiates hues of golden browns and tans, under a delicate butterscotch sky. Beneath this layer lies a grey basaltic planet, its true face concealed by billions of years of chemical weathering. This deception is just the beginning. Mars's secrets run deeper than colour. The Martian dust is not passive, but actively scatters light in unique ways. At sunset, the sky glows blue around the sun, a stark contrast to Earth's fiery twilight hues. This inversion occurs because fine, iron-rich particles, some as small as 1/100th the width of a human hair, absorb blue light during the day and scatter it as the sun dips below the horizon. These particles, remnants of ancient volcanic activity and weathering processes, make Mars a world of opposites, where even the sky defies familiar comprehension. Why is Mars coated in this rusty dust? The answer lies in its tumultuous past, which mirrors Earth's early history, but took a catastrophic turn. Around 4 billion years ago, Mars was a wet world carved by rivers, dotted with lakes, and possibly covered by vast oceans. Ancient riverbeds, deltas, and mineral deposits like hematite and jarosite offer compelling evidence of this vanished era. Today, Mars is a frozen desert, its water locked in polar ice caps or buried beneath the surface. The transition from a potentially habitable world to a desolate landscape is one of planetary science's most enduring mysteries. Around 3.7 billion years ago, Mars's magnetic field collapsed, leaving it vulnerable to solar wind and cosmic radiation. These relentless forces stripped away its atmosphere, causing water to evaporate and leaving iron-rich minerals to oxidize, turning the surface rust-red. This desiccation fundamentally altered Mars's chemistry and geology, yet hints of its watery past remain, suggesting life may have existed or could still persist beneath the surface. Some regions, like the ancient lakebed in Jezero Crater, now host NASA's Perseverance rover, which is searching for signs of microbial fossils in rocks dating back 3.5 billion years. Observation. Martian dust varies dramatically across regions. It forms towering dunes in some areas, such as the dark, wind-sculpted ripples of the Hellespontus region, and smooth, layered deposits in others, shaped by wind and geological activity. The Tharsis region, home to the largest volcanoes in the solar system, hosts massive dust storms that can envelop the entire planet for weeks. These storms, driven by temperature and pressure changes, reshape the landscape dramatically and unpredictably, sometimes depositing dust as far as the planet's poles. Speculation. Could Mars regain its lost atmosphere and water? Terraforming proposals involve warming its surface and releasing carbon dioxide from polar ice to rebuild its atmosphere. While technically and ethically daunting, this vision of restoring Mars fuels scientific imagination. For now, Mars stands as a testament to the fragility of planetary habitability and the relentless forces of change. Recap. Mars is not red, but rust-coloured, with a butterscotch sky and blue sunsets. The dust's origin and the processes that created it remain mysterious. Mars's transformation from a wet, habitable world to a frozen desert reveals the fragility of planets and the profound consequences of atmospheric loss. Mini cliffhanger. To understand the rust, we must explore the water and the catastrophe that reshaped Mars into the world we see today. Part 2. The Lost Ocean. Did Mars once have an ocean? Evidence suggests yes. Ancient riverbeds like Ma'adim Vallis, stretching over 700 kilometers, and deltas at the edges of vast basins hint at past water flow. In 2019, researchers found evidence of massive tsunamis that swept across the Northern Ocean, Oceanus Borealis, billions of years ago. This ocean may have covered a third of Mars's surface, with depths up to 1.6 kilometers, and could have held more water than Earth's Arctic Ocean. Imagine Mars with vast oceans lapping against ancient coastlines. The northern plains, lying 4 kilometers lower than the southern highlands, may have been submerged under this ocean. This would have created a stark contrast, the north resembling Earth's oceans, the south dry and elevated. Today, Mars is a desert with a thin atmosphere, too thin to support liquid water. So where did the ocean go? The answer lies in Mars's lost magnetic field. Observation. Mars's surface holds clues to its watery past. Hematite blueberries discovered by the Opportunity rover in 2004 suggest prolonged interaction with liquid water. Clay minerals formed in neutral pH conditions indicate water that was potentially habitable. Yet Mars is now a frozen wasteland, its atmosphere so thin that exposed water would boil away. Newly discovered shoreline-like features further suggest the presence of an ancient ocean. Interpretation. Mars's transformation from a habitable world to its current state is tied to the loss of its magnetic field. Without this shield, solar wind stripped away up to 90% of Mars's original atmosphere through a process called atmospheric sputtering. As the atmosphere thinned, liquid water evaporated, and the Northern Ocean vanished. This process may have taken millions of years, gradually turning Mars into the desolate planet we see today. Speculation. Why did Mars's magnetic field shut down, The answer may lie in its core. Unlike Earth, Mars lacks a dynamic core to generate a magnetic field. Its core cooled and solidified early, possibly due to its smaller size. Without the motion of molten iron, the magnetic field collapsed, leaving Mars vulnerable to solar wind erosion. Had Mars retained its magnetic field, it might still be a world of oceans and life, with the potential for complex ecosystems to develop over time. Recap: Mars once had liquid water, possibly in a vast northern ocean, but is now dry and cold. The key to this transformation is the loss of its magnetic field. Mini cliffhanger. What happened to Mars's magnetic field? The answer lies deep within the planet's core. Part 3. The magnetic shield. Mars used to have a magnetic field, a powerful and invisible barrier that once protected the planet from the relentless bombardment of solar radiation. This shield, generated by the churning of molten iron in the planet's core, was Mars's first line of defense against the hostile environment of space. We know this because patches of strong magnetization still exist in the Martian crust, particularly in the southern highlands. These remnants are like fossils preserved from a time when Mars had a global magnetic field generated by convection currents in its core. These magnetic signatures, some as strong as 60 microteslas, are scattered across the surface like ghostly echoes of the planet's past. But about 4 billion years ago, something changed. The core cooled, convection stopped, and the magnetic field collapsed. This critical event marked the beginning of Mars's long decline. Without this shield, the solar wind, a stream of charged particles from the Sun, began stripping away Mars's atmosphere, a process that continues to this day. The loss was catastrophic. Over hundreds of millions of years, Mars's atmosphere thinned to less than 1% of Earth's, plunging the planet into a deep freeze. The surface temperature, once potentially warm enough for liquid water, dropped to an average of 63 centigrades, 81 degrees. The oceans evaporated or froze and the water cycle shut down. Some of the water remains locked in ice beneath the surface, particularly at the polar caps, where vast deposits of water ice stretch for thousands of kilometers. However, most of it is gone, lost to space or trapped in hydrated minerals within the rocks, a stark reminder of the planet's once vibrant past. Today, NASA's MAVEN spacecraft measures the ongoing erosion of Mars's atmosphere. The solar wind is stripping away gas at a rate of about 100 grams per second, a seemingly small amount that adds up to a devastating loss over geologic timescales. During solar storms, this rate increases dramatically, with the Sun's coronal mass ejections blasting the planet with up to 10 times the normal amount of charged particles. And in the early solar system, when the Sun was younger and more active, these storms were far more frequent and powerful. Mars was doomed, its fate sealed by the loss of its magnetic shield. Recap: Mars lost its magnetic field about 4 billion years ago, leaving its atmosphere vulnerable to the solar wind. Over time, the planet lost most of its atmosphere and water, transforming into the cold, dry world we see today. The once thick atmosphere, which may have been as dense as Earth's, dissipated into the void, leaving behind a thin, carbon dioxide-rich remnant. Observation: the patches of magnetized crust on Mars are not evenly distributed. They are concentrated in the southern highlands, suggesting that the planet's magnetic field may have been asymmetrical, or that the core's activity was uneven as it shut down. This asymmetry could have contributed to the uneven erosion of the atmosphere, with the northern lowlands losing their protective cover more quickly. Speculation. If Mars had retained its magnetic field, it might still be a warm, wet world today. The presence of a magnetic shield could have protected the atmosphere from solar wind stripping, allowing the planet to maintain liquid water on its surface. This, in turn, could have supported the long-term evolution of life, making Mars a potential second home for humanity. Mini cliffhanger. But the story of Mars's water doesn't end there. Deep beneath the surface, a hidden reservoir may still exist, offering a glimmer of hope for the planet's future and our own. Part 4. The Hidden Ocean. Mars conceals liquid water in a vast subsurface reservoir, not the ancient surface water of billions of years past, but a stable, briny layer trapped deep below. In April 2025, NASA's InSight lander unveiled this discovery. Seismic data indicated a liquid water layer 5.5 to 8 kilometers down, potentially enough to cover Mars in an ocean up to 780 meters deep, nearly half the volume of Earth's Atlantic Ocean. While previous observations hinted at buried water ice and occasional briny flows, InSight provided the strongest evidence for a planet-wide aquifer system, fed by ancient water trapped in Mars's porous crust. This water is far from potable. It's a salty mixture of perchlorates and chlorides, with salinity levels up to 5 times higher than Earth's oceans. Yet its existence challenges our perception of Mars as a dry, desolate world. The planet may harbour remnants of its ancient hydrological cycle, hidden beneath its dusty, frigid surface. This discovery reframes Mars's potential habitability. On Earth, microbes thrive in similar deep, chemically active environments, like the hypersaline Dead Sea or Antarctica's briny pools. If life emerged during Mars's warmer, wetter past, it could persist today, sheltered in the subsurface, sustained by liquid water and shielded from cosmic radiation. Observation. Mars's surface is inhospitable, but kilometers below, conditions could be surprisingly livable. Temperatures near internal heat sources might reach 60 degrees C, 140 degrees, ideal for thermophilic microbes. These heat sources could include dormant volcanic regions like Tharsis Montes or areas with residual geothermal activity, where temperatures might locally exceed 100 degrees C, 212 degrees Celsius. Interpretation: liquid water doesn't guarantee life, but it makes it plausible. Life requires water, energy, and chemical building blocks. Mars seems to offer all three in isolated pockets: subsurface water for habitat, geothermal heat for energy, and carbon-rich meteorites for organic compounds. Perchlorate salts, once thought toxic, might even serve as an energy source for certain microorganisms, as seen in Earth's extremophiles. Speculation: Martian life, if it exists, may not be confined underground. Briny water could occasionally seep to the surface, creating temporary habitats like the recurring slope lineae, dark streaks possibly formed by seasonal water flows. These streaks hint at a dynamic water cycle still at work today. Could these oases host microbial life during Mars's fleeting warm seasons? Future missions like ESA's Rosalind Franklin rover may uncover the truth by drilling into the Martian subsurface. Mini cliffhanger. Does life persist on Mars today? The answer may lie in the planet's turbulent history and its faint but persistent geological activity. To unravel Mars's potential for habitability, we must explore its past cataclysms, the whispers of its restless interior, and the tantalizing possibility that the red planet is not as dead as it seems. Part 5. The Shaking Planet. Mars may be quiet, but it's far from dead. Beneath its still surface lies persistent geological activity, driven by the planet's slow cooling. This activity is subtle, unlike Earth's dynamic systems, but it's steadily shaping the planet. The red planet's geology is a slow-motion drama unfolding over millions of years, with forces strong enough to crack the crust and send tremors through the silent landscape. On May 4, 2022, NASA's InSight lander recorded the largest Marsquake ever, a magnitude 4.7 event. Initially suspected to be a meteorite impact, further analysis revealed no crater. The quake was tectonic, originating deep within Mars, proof of the planet's ongoing geological processes. This event lasted over an hour and a half, with waves reverberating through the planet's interior, offering scientists an unprecedented opportunity to probe Mars's deep structure. Mars lacks Earth-like plate tectonics, but has a stagnant lid system, where the crust is a thick, mostly stationary plate. Internal heat from its formation 4.5 billion years ago creates stresses that release as Marsquakes. InSight detected over 1,300 quakes during its operation, unveiling Mars's active geology despite its calm appearance. These quakes were mostly low-frequency, long-duration events, painting a picture of a planet creaking and settling under the weight of its own history. A notable discovery was a quake triplet, 3 nearly identical quakes from Cerberus Fossae, a tectonically active region. This fault system, with deep fissures and evidence of recent volcanic activity, is one of Mars's most dynamic areas, hinting at possible subsurface liquid water. Cerberus Fossae stretches over 1,600 kilometers, a gash in the Martian surface that speaks to the immense forces at work. The triplet quakes, originating from the same spot, suggested a localized area of intense activity, perhaps a buried magma chamber or a pocket of pressurized water. Observation. Marsquakes offer a seismic window into the planet's interior. The speed and behavior of seismic waves have mapped Mars's crust, mantle and core, revealing a thinner than expected crust, a complex mantle and an active core contributing to its magnetic field. The crust, averaging about 24 kilometers thick, is denser than expected, hinting at a composition rich in heavier elements like iron. The mantle shows signs of layering, with different zones that may reflect varying levels of hydration or composition. Speculation. Could Mars's geological activity support life? On Earth, life flourishes in geologically active zones like hydrothermal vents. If Mars has similar subsurface conditions powered by its internal heat, microbial life could potentially survive there. Marsquakes suggest such environments might exist. The presence of methane gas detected in the Martian atmosphere adds to this speculation. Methane could be produced by geological processes, but on Earth it is also a byproduct of life. If Mars has subsurface hydrothermal systems, they could be havens for chemotrophic organisms, using the planet's internal heat as an energy source. Recap. Mars is geologically active with ongoing tectonic stresses releasing as Marsquakes. The planet is cooling and adjusting with a partially molten core and dynamic fault systems. Seismic data from InSight show a world in slow, steady evolution. The data also hint at a past when Mars was even more active, with volcanoes towering 3 times higher than Earth's Everest, and vast floods carving channels that dwarf the Grand Canyon. mini cliffhanger. But Mars's activity isn't confined to its core. Its surface holds a toxic legacy, shaped by its geological past and present harsh conditions. As we explore further, what secrets will we uncover beneath its shaking surface? Could the answers to life's existence on Mars lie not in its skies or ice caps, but deep within its restless heart? The planet beckons, its mysteries pulsing beneath every tremor and quake. Part 6. The toxic soil. Mars' red surface hides a toxic secret. In 2008, NASA's Phoenix lander conducted a chemistry experiment, mixing Martian soil with Earth water. The pH was 8.3, slightly alkaline, similar to garden soil, but the sample contained perchlorates, salts of chlorine and oxygen. While rare on Earth, perchlorates are ubiquitous on Mars, making up as much as 1% of the soil composition in some regions. These compounds are so prevalent that they are detectable even from orbit, appearing as distinct spectral signatures across vast swaths of the Martian surface. Perchlorates disrupt thyroid function in humans, leading to severe health issues with prolonged exposure. For plants, they are devastating, reducing chlorophyll production and stunting growth. At concentrations found in Martian soil, most Earth plants cannot survive. This toxicity also affects microorganisms, making the soil inhospitable to life. The absence of organic matter in Martian soil samples further underscores this stark reality. When heated, perchlorates can react explosively, posing additional risks for any equipment designed to process or handle Martian soil. High UV radiation on Mars worsens the problem, breaking down perchlorates into even more harmful compounds. These substances are up to 10 times more lethal to bacteria, sterilizing the soil's top layers. This toxicity poses a major challenge for human exploration and habitation. The UV exposure on Mars is approximately 250 times stronger than on Earth, as Mars lacks a protective ozone layer. This intense radiation not only exacerbates soil toxicity, but also damages any unprotected organic material, further reducing the chances of surface life. Martian dust is extremely fine, clinging to surfaces and infiltrating machinery. Astronauts will inevitably bring this dust into habitats, and its small size, about 100 times smaller than a grain of sand, makes it easily inhaled. Long-term exposure could lead to chronic lung conditions. The dust's composition, rich in iron oxide, also makes it magnetically reactive, complicating efforts to keep it out of sensitive equipment. Its abrasive nature accelerates wear and tear on mechanical systems, posing a constant threat to rovers and future habitats. Observation: Martian soil toxicity isn't limited to perchlorates. Rovers like Curiosity and Perseverance have detected heavy metals and reactive oxygen species. These compounds further complicate human exploration, as Martian dust's high iron oxide content makes it highly reactive when exposed to water, potentially damaging equipment. The presence of calcium perchlorate in particular raises concerns, as it can absorb water from the atmosphere and form briny solutions that are even more toxic to microorganisms. Speculation: the toxic nature of Martian soil may explain the lack of surface life. While Mars may have been habitable in the past, perchlorates and UV radiation could have sterilized the soil over billions of years. However, life may still exist beneath the surface. Future missions aim to drill deep into the Martian subsurface to search for signs of life. The European Space Agency's Rosalind Franklin rover slated to launch in the late 2020s, will drill up to 2 meters below the surface, probing regions shielded from the harsh conditions above. Recap: Martian soil is toxic, contaminated with perchlorates and other harmful substances that pose risks to human health and plant growth. High UV radiation makes the soil even more dangerous, complicating efforts to establish a sustainable presence on Mars. The fine, reactive nature of Martian dust adds another layer of difficulty, threatening both human health and the functionality of critical machinery. Mini cliffhanger. But the toxic soil is just one piece of the puzzle. The real danger lies in the dust and the storms that carry it. Part 7. The dust storms. Mars, despite its thin atmosphere, experiences powerful weather phenomena, including vast dust storms that can stretch thousands of kilometers and tower up to 60 kilometers high. These storms can endure for months, obscuring the landscape and reshaping Mars's climate. During the 2001 global dust storm, atmospheric temperatures spiked by 30 degrees, 54 Fahrenheit, highlighting their dramatic impact. Martian dust storms are far more intense than Earth's dust devils, capable of blanketing entire regions and persisting for extended periods. In 2018, a planet-wide storm disabled the Opportunity rover by depriving it of sunlight, ending its 15-year mission. This event lasted over 4 months and covered an area larger than North America and Russia combined, altering the landscape and redistributing water ice at the poles. The dust on Mars is electrically charged, clinging to surfaces and creating risks for exploration. It can infiltrate machinery, obscure solar panels, and pose respiratory hazards to future astronauts. During the Apollo 17 mission, lunar dust, less reactive than Martian dust, still caused significant issues. On Mars, the problem would be far worse due to the dust's electrostatic properties and finer size. However, the dust offers insights into Mars's past. The planet's reddish color comes from iron oxide, a result of billions of years of weathering. This thin layer of rust conceals dark basaltic rock beneath. The dust also influences Mars's climate by altering its albedo, leading to extreme temperature swings during storms, sometimes dropping to 100 degrees Celsius, 148 degrees, at night. Observation: Mars's dust storms are tied to its orbital cycles and seasonal changes. They frequently occur during the southern hemisphere's spring and summer, when solar heating lifts dust from the surface. In 1971, Mariner 9 arrived at Mars to find the planet engulfed in a global dust storm, delaying surface imaging for over a month. Speculation: could dust storms have played a role in Mars's water loss? By absorbing solar radiation, fine dust particles may have heated the upper atmosphere, accelerating the escape of water vapor. This process, combined with Mars's lack of a magnetic field, could have transformed the planet from a wet world into the desert we see today. Recap: Mars's dust storms last for months, posing risks to exploration, but also offering clues to the planet's history. The electrically charged dust threatens machinery and human missions, yet it holds secrets to Mars's transformation over billions of years. For example, its interaction with water ice at the poles could reveal insights into the planet's climatic past. Mini cliffhanger: the dust is more than a challenge. It's a window into Mars's past. Could understanding these storms help us uncover the secrets of a planet that may have once resembled Earth, and might harnessing the dust pave the way for future human settlements on Mars? Part 8. The Rusty Planet. Why is Mars covered in iron oxide dust? The answer is surprisingly complex. Rust forms on Earth when iron reacts with oxygen and water, but Mars has almost no free oxygen in its atmosphere. Its air is primarily carbon dioxide, with oxygen making up only about 0.13% compared to Earth's 21%. So how did all that iron get oxidized? There are several possibilities, and all of them could be happening at once. One process involves a direct chemical reaction between iron and water. When water comes into contact with iron-containing minerals, it can oxidize the iron without any free oxygen being present. This reaction is thermodynamically unfavorable under normal conditions, but it can be sustained if the hydrogen gas produced by the reaction escapes quickly into the atmosphere. On Mars, with its thin atmosphere, just 1% the pressure of Earth's, and low gravity, hydrogen escapes easily, allowing the reaction to continue. This process has likely been ongoing for billions of years, as Mars's once abundant water interacted with its iron-rich surface. Another process involves hydrogen peroxide. Though rare in the Martian atmosphere, hydrogen peroxide is a powerful oxidizing agent. Laboratory experiments show that it can oxidize iron minerals efficiently, producing the same ferrous oxides we see in Martian dust. Hydrogen peroxide could have formed in the Martian atmosphere through the interaction of ultraviolet light with water vapor, a process observed by NASA's Mars Odyssey spacecraft. The presence of hydrogen peroxide could also explain why some regions of Mars appear more oxidized than others, as its distribution is uneven across the planet. There's also evidence that mechanical erosion plays a role. Experiments at the Mars Simulation Laboratory in Denmark show that when a mixture of magnetite powder and quartz dust is tumbled together, some of the magnetite converts to hematite, the red iron oxide that gives Mars its color. This means that wind-blown dust storms on Mars, which are frequent and can last for months, might be continuously producing more rust simply through the mechanical grinding of rocks against each other. These storms can reach speeds of up to 60 miles per hour, scouring the surface and transforming the landscape over time. The dust they generate is so fine, about 3 microns in diameter, that it can remain suspended in the atmosphere for weeks, tinting the sky a faint reddish hue. Recap: the iron oxide dust that coats Mars is the product of billions of years of chemical weathering and mechanical erosion. These processes have created a thin layer of rust that colors the sky and hides the planet's true face. The dust is not just a visual feature, it also plays a critical role in Mars's climate. It absorbs solar radiation, warming the atmosphere and driving weather patterns. It can even block sunlight from reaching the surface, cooling the planet during global dust storms. This delicate balance of heating and cooling shapes Mars's seasons and influences the behavior of its polar ice caps, which are composed primarily of water ice mixed with dust. Observation: some of the most striking evidence of Mars's rusty past comes from the Spirit and Opportunity rovers, which landed on opposite sides of the planet in 2004. Both rovers discovered small, spherical formations known as blueberries, hematite-rich concretions that formed in the presence of water. These blueberries, some as small as BB pellets, are scattered across vast regions of the Martian surface, providing a tangible record of the planet's wet, oxidizing history. They also hint at a time when Mars may have been more hospitable to life. Mini cliffhanger. But the rust is just the beginning. Beneath it lies a world of contradictions and possibilities. The question of whether Mars ever harbored life is inextricably linked to its rusty surface, as the same processes that oxidized its iron may have also created conditions suitable for microbial life. The search for answers continues as rovers like Perseverance drill into the Martian crust, seeking clues in the layers of dust and rock that tell the story of the red planet's transformation. Part 9. The Buried Secrets. In 2017, NASA's Curiosity rover made a disturbing discovery in Gale Crater. The rover had been studying layers of mudstone, ancient sediment deposited at the bottom of a lake billions of years ago. These layers should have been rich in clay minerals which form in the presence of water and preserve a chemical record of environmental conditions. The mudstones, finely laminated and bearing witness to Mars's wetter past, were once submerged under a lake that could have spanned an area roughly the size of Connecticut. But in some locations, about half the clay minerals were missing. Instead of clays, Curiosity found mudstones rich in iron oxides, the same rusty minerals that give Mars its red color, a stark reminder of the planet's desolate present. The culprit was brine, super salty water that seeped down through cracks in the overlying rock layers long after the mudstones formed. This briny groundwater dissolved the clay minerals and redeposited iron oxides in their place. The process is called diagenesis, a kind of chemical rewriting that happens underground when water moves through rocks, dissolving some minerals and precipitating others. Imagine the slow, relentless trickle of brine infiltrating the porous mudstone, altering its composition over millions of years. Diagenesis creates an underground environment that can actually support microbial life. On Earth, some of the most extreme habitats, where bacteria thrive deep beneath the surface, far from sunlight, are powered by diagenetic processes. In places like the deep sea bed of the Atlantic, microbes metabolize minerals dissolved by diagenesis, sustaining entire ecosystems in the dark. But diagenesis also erases evidence. Clay minerals are like time capsules, preserving a record of the water chemistry, temperature, and pH when they formed. They can even preserve organic molecules, the chemical signatures of life. When diagenesis replaces clays with iron oxides, that record is lost. The evidence disappears. This is a problem for the search for ancient life on Mars. We know that Gale Crater once held a lake, and the environment was potentially habitable. The lake may have persisted for tens of millions of years, long enough for life to emerge and evolve. But in some places, the evidence of what actually happened in that lake has been chemically erased and overwritten. And scientists estimate that up to 70% of the original clay minerals in certain layers have been altered, leaving behind a geological puzzle with missing pieces. Observation: the iron oxides left behind by diagenesis are not entirely useless. They can indicate the presence of past water and provide clues about the chemistry of that water. However, they lack the detail and specificity of clay minerals, making it harder to reconstruct the ancient environment. Speculation: if life did emerge in Gale Crater, it may have adapted to the changing conditions caused by diagenesis. Microbes on Earth have evolved to survive in briny, mineral-rich environments. Could similar life forms have once thrived in the altered mudstones of Mars, leaving behind faint traces still waiting to be discovered? Recap: diagenesis, the chemical rewriting of rocks by briny groundwater, has erased some of the evidence of Mars's watery past. This process has both created and destroyed potential habitats for microbial life. The rusty iron oxides that now dominate the landscape are a testament to the planet's complex geological history and the challenges of uncovering its secrets. Mini cliffhanger. But the search for life on Mars is far from over. The next breakthrough may come from an unexpected source, hidden in the layers of time or buried beneath the red sands. Part 10. The Search for Life. Could life have existed on Mars? This question has captivated scientists for centuries. Evidence suggests it is plausible. Mars once had liquid water, including an ancient ocean that may have covered a third of its northern hemisphere. This body of water, up to a mile deep, could have supported life. Over 3.5 billion years ago, rivers may have flowed across Mars, feeding into vast lakes and seas under a thicker, warmer atmosphere. In 2019, NASA's Perseverance rover drilled into a rock called Shiava Falls in Jezero Crater, an ancient lake bed. The rover extracted a sample, Sapphire Canyon, a pencil-thin core containing potential biosignatures, traces of ancient microbial life, such as organic compounds and possible microfossils. These microfossils, if confirmed, would mark the first evidence of extraterrestrial life. However, the findings remain inconclusive. Organic compounds could result from non-biological processes, and spherical structures resembling microfossils might be mineral precipitates. Perseverance's Sherlock instrument, though advanced, lacks the precision to definitively distinguish biological from abiotic origins. NASA and ESO are planning a Mars sample return mission to resolve this. Perseverance has collected 28 samples in titanium tubes, which will be analyzed on Earth with more sensitive tools, like the Mars Organic Molecule Analyzer, MOMA. This instrument could examine the handedness of molecules, potentially providing conclusive evidence of life. Meanwhile, Perseverance continues exploring the Martian terrain for additional clues. Even if Sapphire Canyon lacks proof of life, it doesn't rule out past or present Martian life. Most of Mars remains unexplored, especially its subsurface. If life exists today, it likely resides deep underground, shielded from the harsh surface conditions. On Earth, extremophiles like Deinococcus radiodurans thrive in such environments. The ExoMars rover, Rosalind Franklin, equipped with a 2-meter drill, could uncover such life when it launches in 2028, probing depths untouched by previous missions. Beyond the search for life, Mars offers insights into habitability itself. Billions of years ago, it may have been warmer and wetter, but the MAVEN spacecraft revealed that solar wind and radiation stripped away 99% of its original atmosphere. This transformed Mars into the cold desert we see today. Understanding this process could shed light on Earth's atmospheric stability and the delicate balance required for life. If life existed on Mars, did it adapt and retreat underground as the climate changed? Could it still be there? Answering these questions could reshape our understanding of life in the universe. Independent life on Mars would suggest that life emerges naturally given the right conditions, raising possibilities for life elsewhere, such as on the icy moons of Jupiter and Saturn. The search for life on Mars continues. Perseverance's samples may hold biosignatures, but confirmation requires Earth-based analysis. The subsurface remains a promising frontier for life, and future missions like ExoMars will explore these depths. Yet Mars holds other mysteries too. Its moons, Phobos and Deimos, may offer clues to its past and the solar system's evolution. As humanity's quest for knowledge expands, Mars stands as a beacon, slowly yielding its secrets to science. Part 11. The falling moon, Phobos is falling. Mars has two moons, Phobos and Deimos. Both are small, irregularly shaped, and probably captured asteroids. Deimos orbits at a safe distance of 23,460 kilometers from Mars, taking just over 30 hours to complete a single orbit. But Phobos is different. It orbits just 9,377 kilometers above the Martian surface, closer to its planet than any other moon in the solar system. This proximity means Phobos completes an orbit every 7 hours and 39 minutes, faster than Mars rotates. This makes Phobos one of only 18 moons in the solar system, whose orbital period is shorter than its planet's day. From the surface of Mars, Phobos appears to rise in the west and set in the east, crossing the sky twice in a single Martian day. Its rapid motion would be a striking sight to future astronauts or settlers, appearing as a swiftly moving star against the Martian night, casting faint but distinct shadows that sweep across the rust-red landscape. The moon's proximity also makes it a tantalizing target for future missions, as its low gravity and weak surface make it easier to land on and study. Already, space agencies have proposed missions to land on Phobos, collect samples, and even use it as a staging ground for further exploration of Mars. Tidal forces between Mars and Phobos are causing the moon's orbit to decay. Phobos is spiraling inward at a rate of about 2 centimeters per year. Though this movement is slow on human timescales, it is inevitable and catastrophic on geological ones. In 20 to 40 million years, Phobos will reach the Roche limit, the distance at which tidal forces will overcome the moon's self-gravity and tear it apart. When Phobos reaches the Roche limit, the tidal forces will be strong enough to pull the moon apart. The regolith layer, about 100 meters of loose, powdery material, will be stripped away first, spreading into a ring around Mars. This process will be gradual but spectacular. The ring will be dark, composed of carbon-rich dust and rock, the same material that makes up Phobos. It will be relatively narrow at first, but over time it will spread out, reaching down into the upper Martian atmosphere within a few million years. The ring will cast shadows on the Martian surface, creating a subtle but detectable change in the planet's lighting conditions. Eventually, the material will rain down onto the surface, creating a slow shower of meteors that could last for millions of years. As the debris enters the atmosphere, it could produce faint but persistent meteor showers, streaking across the Martian sky in a display that would be visible even from the planet's surface. The larger chunks of Phobos will fall as well, impacting Mars and creating chains of elongated craters along the equator. These impacts will reshape the Martian surface, gouging out new craters and altering the landscape in ways that could affect future habitability. Some of these craters could measure hundreds of meters across, leaving enduring scars on the red planet. The debris from Phobos will also introduce new material into the Martian atmosphere, potentially altering its composition and behavior. Dust storms could become more frequent or intense as Phobos's material mixes with the fine Martian dust, further complicating the planet's already dynamic weather patterns. The introduction of new material could also trigger chemical reactions in the atmosphere, potentially producing temporary increases in water vapor or other compounds that could influence the planet's climate. Mars will have a ring system for somewhere between 1 million and 100 million years, and then it will fade as the debris falls to the surface, Deimos will remain alone, the last moon of Mars, its lonely orbit a reminder of the planet's cyclical history. This has probably happened before. Some planetary scientists think Mars once had more than 2 moons. Simulations suggest that earlier generations of moons spiraled inward, broke apart, and rained down on the surface. The pattern repeats on geological timescales. When Phobos falls, it will be continuing a cycle that may be billions of years old. The remnants of these past moons could still lie buried beneath the Martian surface, waiting to be discovered by future missions. These buried fragments could provide critical clues about the history of Mars and its moons, offering insights into the planet's geological and atmospheric evolution. Recap. Phobos, one of Mars's 2 moons, is spiraling inward and will eventually be torn apart by tidal forces, creating a temporary ring system around the planet. This cycle may have repeated multiple times in Mars's history. Observation. The gradual decay of Phobos's orbit offers a rare opportunity to study tidal forces and orbital mechanics in real time, providing valuable data for planetary scientists. Mini cliffhanger. But the story of Mars's moons is not just about the past, it's about the future and the role they may play in human exploration. Part 12. The future of Mars. Mars is not insurmountable. Yes, the planet is hostile. The soil is toxic, contaminated with perchlorates at levels that would be dangerous to humans. These salts, used in rocket fuel and fireworks on Earth, lower the freezing point of water, allowing it to remain liquid at Mars's frigid temperatures. The atmosphere, a thin blanket of mostly carbon dioxide, provides almost no protection from cosmic radiation. The temperature swings are extreme, from a high of 20 degrees, 68 degrees at noon, to 153 203 degrees at the poles. And the dust storms can last for months, covering half the planet in a haze that blocks out the sun, turning day into a ruddy twilight. These storms can also become global events, as witnessed by NASA's Opportunity rover in 2018, which was overwhelmed by a planet-wide tempest that blocked out the sun for weeks. But it's also not impossible. NASA's Perseverance rover has demonstrated that Martian regolith contains accessible water with hydrated minerals and even briny aquifers beneath the surface. Engineers are developing systems like MOXIE, Mars Oxygen In Situ Resource Utilization Experiment, to extract oxygen from the carbon dioxide atmosphere, achieving a production rate of 6 grams per hour, enough to sustain a small dog. Biologists have identified extremophile bacteria on Earth that can break down perchlorates and even use them as an energy source, opening the possibility of bioremediation for Martian soil. Architects are designing habitats that could be built underground, shielded from radiation by layers of rock, or using inflatable structures covered with regolith for protection. Mars is a laboratory, a place where we can study planetary evolution, atmospheric loss, and the limits of habitability. It's also a mirror, reflecting back a version of what Earth could become if conditions change, or what Earth once was in its earliest days before life transformed the atmosphere. The Arctic permafrost on Earth, for example, contains methane clathrates, a potential analogue for Martian subsurface processes. The more we study Mars, the more we learn about our own world. For instance, understanding Mars's past liquid water could inform our models of climate change on Earth. Right now, NASA's Perseverance rover is driving across the floor of Jezero crater, collecting samples that could contain evidence of ancient microbial life. The Curiosity rover is climbing Mount Sharp, analyzing layers of sediment that span billions of years, revealing a history of water activity and potential habitability. The InSight lander has finished its mission, but the seismic data it collected will be analyzed for decades, providing insights into Mars' internal structure and tectonic activity. Overhead, 8 spacecraft orbit Mars, including ESA's Mars Express and NASA's Mars Reconnaissance Orbiter, imaging the surface, measuring the atmosphere, and mapping subsurface water ice. These orbiters have identified thousands of sites for future exploration, including potential caves that could serve as natural shelters for human habitats. Why did the magnetic field collapse? Was it inevitable, or could it have been prevented? How long did the oceans last? What was the climate like? Could life have arisen in those oceans? If it did, is it still there, hidden underground? We don't know yet, but we will. The samples Perseverance is collecting will come back to Earth in the 2030s as part of the Mars Sample Return Mission, a collaboration between NASA and ESA. Those samples will be studied in laboratories with instruments that can detect organic molecules at parts per trillion concentrations. They'll be able to identify isotopic signatures of biological processes, such as the ratio of carbon-12 to carbon-13, which differs in biological and abiotic samples. They'll be able to date minerals to within a few million years using techniques like potassium-argon dating. If there's evidence of ancient life on Mars, we'll find it. And if we don't find it in those samples, we'll keep looking, because Mars is huge. We've explored less than 1% of its surface, an area roughly the size of Earth's continents, and we haven't even begun to explore the subsurface, where liquid water might still exist. Observation. The discovery of methane plumes on Mars, detected by both the Curiosity rover and orbiting spacecraft, suggests ongoing geological or biological activity.